Hello, welcome back. Now, in this video, we shall discuss the distributions of probability distributions of functions of a random variable. We shall discuss first discrete random variables and then we will come to continuous random variables. In discrete random variables, the procedure is very easy for any defined function. And before that, you know that if x is a discrete random variable and y is a function of that discrete random variable x, then y itself is a random variable. You might have studied this idea in your probability theory. Any function, any real function of a random variable is again a random variable. Okay. Then you can talk about the probability mass function, cumulative distribution function, expected value, etc. of such a function y. And first we note the range of y, the new random variable defined by g of x, y is equal to g of x. And for that purpose, you must know what is the range of x first. If the range of random variable x is known, which you denote this by script x. For example, suppose x is a Poisson random variable, you know that script x is equal to set of 0, 1, 2, 3, etc. up to infinity. Whereas for binomial distribution, the script x is 0, 1, 2, 3, etc. n. In the Poisson case, it is a denumerable infinity, whereas in binomial distribution, it is a finite set. Okay. And by taking the range of x, that is script x, you can define the range of y, which we may denote by script y. And what is script y? What is the range of y? It is the value of the function g of x for all x in the range of x. Okay, so this is the definition of the range of a new random variable y. That is the transformed random variable y of x. Okay, and suppose px is the probability mass function of x, then we can find the probability mass function of y. This can be done only by enumerating the probabilities for various values of y in the range script y. Okay, it is only a very simple procedure which we need to list all the probabilities corresponding to the points in the script y. That's all. And that is a very easy procedure. I will give you an example before that. How would you find the probability mass function of y using the probability mass function of x? That is, how would you find p of y using p of x? And here both are used by the letter p, but the suffix x is given here to emphasize that this is the PMF of x, and where the suffix capital Y is given for emphasizing the probability mass function of y. And you can directly compute probability mass function of y. What is probability mass function of y? It is equal to probability that y takes the value y. Okay, that is probability that what is y? Y is g of x, so it is probability of g of x is equal to y. And this is only the sum of all probabilities for which g of x is equal to y. Okay, so it is a sum of p of x where x takes a value such that g of x is equal to y. And this is so for any y. You may take each y, y1, y2, y3, etc. You can compute this probability, and the list of these probabilities for various values of y will give you the probability mass function of y. Okay, and this example will help you to grasp the idea what we have used here. Let x be a random variable, discrete random variable with the probability mass function p of x is equal to probability that x equal to 1 by 5. It is a uniform distribution actually, because for all x minus 1, 0, 1, 2, 3, etc., probability is same, equal to 1 by 5. That is why I call it a uniform distribution, a discrete uniform distribution. And let us define a function y is equal to g of x, which is equal to 2 times modulus of x. Here g of capital X equal to 2 times modulus of x. You can use this notation. Okay, y is equal to g of x. So g of x is equal to 2 into modulus of x. Okay, then what is the range of y? A range of x is script x, which is a set of minus 1, 0, 1, 2, 3. And similarly, script y, which is the range of the new random variable y, is nothing but 2 into modulus of x for x equal to minus 1, 0, 1, 2, 3, etc. In this way, you can find the range of y, which is equal to 2 into modulus of minus 1, because x may take minus 1. Then 2 into modulus of 0, because x may take 0, x may take 1. So the next possible value of y is 2 into mod 1, then 2 into mod 2, 2 into mod 3, etc. And you evaluate these things. This is 2, 0, 2, 4, 6. And 2 is repeated. So in this set, you need not repeat 2. So set 0, 2, 4, 6. So these are the possible values. 0, 2, 4 and 6 are the only possible values of the new variable capital Y when the original variable x takes the value minus 1, 0, 1, 2, 3. Here you can note that x takes 1, 2, 3, 4, 5 values, whereas y takes only 4 values. For this particular example, y is equal to 2 into mod x. Okay, now you see how the probability mass function of y is obtained. That is py of y, that is equal to probability that y takes the value y4, y is equal to 0, 2, 4 and 6 is defined as follows. Py of 0, that is probability that y takes the value 0, that is only probability that x takes the value 0, because y takes the value 0 only when x takes the value 0. So there is only one component, and it is equal to 1 by 5. Whereas the probability that y takes the value 2, see, probability that y takes the value 2, that is probability that y equal to 2, that is equal to probability that x equal to minus 1 or x equal to 1. So there are two possibilities for x, for which y is equal to 2. So when x takes the value minus 1, y is equal to 2, and when x takes the value 1, then also y is equal to 2. Therefore, you have to utilize the probability that x equal to minus 1 and probability that x equal to 1. You have to add them, because you can take either x equal to minus 1 or x equal to 1. So this is equal to probability that x equal to minus 1 is 1 by 5 plus probability that x equal to 1, that is equal to 1 by 5, which is equal to 2 by 5. So you are adding these things. Okay, this addition, this type of addition is expressed here. Okay, this is the summation for all x for which g of y is equal to y. Okay, in this way you can find the probability that y takes a value 4 also. What is probability that x takes a value 2, and there is only one case, x equal to 2, when you can have y is equal to 4. Therefore you need to take only that value 1 by 5. Similarly for probability that y is equal to 6, that also equal to probability that x equal to 3, which is equal to 1 by 5. Okay. So you have obtained the probability for various values of y equal to 0, y equal to 2, y equal to 4, and y equal to 6. So you can consolidate the probability mass function of y as follows. That is, py of y is equal to 1 by 5. In 3 cases, it is equal to 1 by 5. That is when y equal to 0, then y is equal to 4, and y is equal to 6. Okay, only in the case when y is equal to 2, you take p of y is equal to 2 by 5, and there is no probability for other values other than 0, 2, 4, and 6. That is why I am writing finally equal to 0 otherwise. Okay, so you see that for discrete random variables, the distribution of function of a discrete random variable is easy to obtain. That requires only some counting procedure, counting of probabilities. Okay, counting of the possible values of the new variable y, which is a function of the original random variable x. Okay, but for continuous situation, it is not so direct. It requires something other than counting. Okay, and you will see in continuous random variables, we have 2 procedures for finding the probability distribution. The first method is to find the cumulative distribution function, or simply distribution function of the new variable y, and you can differentiate that cumulative distribution function in order to get the probability density function. Okay, that is one procedure, and you can find the cumulative distribution function. In many cases, it can be possible to find the cumulative distribution function directly. You see here, if x is a continuous random variable, y is equal to g of x, which is a function of x, and y is a random variable. As in the case of a discrete random variable, here also the function, any real function, is a random variable. Okay, and you can proceed to find the cumulative distribution function of the new variable, transformed variable y, and then differentiate that cumulative distribution function. Okay, that is the procedure of, it is a direct procedure. And one more procedure is there that I will discuss in the next part of this lecture. Okay, you come to an example. This example will illustrate how, using the distribution of x, the cumulative distribution of y can be determined, and then the density function of that y can be determined by differentiating the cumulative distribution function. Okay, now in this example, I take x follow a uniform distribution over 0, 1. Uniform distribution over 0, 1 means what is the density of x? It is equal to 1 in the range 0 to 1 and 0 elsewhere, and the graph of that density is also given for your easy reference. Okay, now uniform 0, 1, this is a notation for expressing a uniform, continuous uniform distribution, and we have to find the distribution of y, which is equal to e to the power of x. Okay, and here g of x is e to the power of x, because y is defined as a function of x, and that function of x can be put as g of x, which is equal to e to the power of x. Okay, and the distribution of y can be determined as in this example. You know the density function of x. Okay, that is very simple, and you can find the cumulative distribution function of x, which is equal to probability that x less than or equal to x, which is 0 to x fx dx, that is 0 to x dx, because f of x is 1, and it is equal to x in the range 0 to 1. And you know, for cumulative distribution function, when x is less than the lower limit, f of x is 0, and when x is greater than the upper limit, f of x is equal to 1. These things are very obvious from the property of a distribution function. So distribution function will be therefore written as distribution function of x equal to 0 if x is less than 0, and x when x lies between 0 and 1, and for all x greater than 1, f of x is equal to 1, and the graph of that f of x is also given for your reference. Okay, and what you have? Distribution function of x. And now we come to the range of y, new variable y. What is the range of new variable? It is nothing but the set of all e to the power of x for x lying between 0 and 1. And you know that the range of new variable is 1 to e, because when x takes the value 0, you take e to the power of 0, that is equal to 1, and when x takes the upper value 1, e to the power of 1, which is equal to e. So the range can be easily written as a script y, that is equal to 1 to e. Therefore y varies from 1 to e. Y varies from 1 to e. And you know, the distribution function will have value 0 below 1, and above e distribution function will be equal to 1. Okay, f of y, probability that y less than y equal to 0 for y less than 1, and f of y which is equal to 1 for y greater than or equal to e. This result is actually a very obvious result for any distribution function. That is, for any distribution function, it will have value 0 when y is below the lower limit of the or lower range, and it is equal to 1 when y is above the upper range. Okay, and we have to find the value of f of y in between 1 and e. What will happen f of y when y takes a value between 1 and e? That you can find like this. For y 1 less than y less than e, we have fy of y is equal to probability that this is a usual way of finding f of y. Probability that y takes the value less than or equal to y, that is probability that you can simply write, because y is equal to e to the power of x. So probability that y less than or equal to y equal to probability that e to the power of x less than or equal to y. Okay, and you can see that e to the power of x is an increasing function. It is an increasing function. E to the power of x is an increasing function in x. Therefore, this e to the power of x less than or equal to y can be equivalently written as x less than or equal to log of y, because you are taking logarithm on both sides. Okay, and therefore x less than or equal to log of y. Right, and you can see this is what is this? What is this? Probability that x less than or equal to log y means fx of log y. By definition, it is fx of log y. And what is fx of log y? Fx of log y is, you see, fx of x is x. Fx of x is x in the range 0 to 1. Okay, therefore, what is the argument in the function? The same argument is given here, x. In that way, f of x log y is nothing but log y, since log y lying between 0 to 1. So we have found the final expression for the distribution function of y as which is equal to 0 for y less than 1. We have determined earlier. Then f of y is equal to 1 for y greater than or equal to e, and fy of y is equal to log y 1 less than or equal to y less than or equal to e. Okay. Now in this way you can determine the distribution function. And actually this solution of the distribution function of y is a roundabout way. Sometimes you can feel so. And you can find Fy of y directly. Fy of y directly. How? Fy of y, that is equal to probability that y less than or equal to y, that is equal to probability that e to the power of x less than or equal to y, that is equal to probability that x less than or equal to y, and probability that x less than or equal to y you can express in terms of an integral. In terms of an integral. How would you write this? If this is expressed as an integral, what will be this? It is equal to my integral from എക്സിൻ്റെ ലോവർ ലിമിറ്റ് 0 ആണ്. അപ്പോൾ ഇത് ഇവാലുവേറ്റ് ചെയ്യുമ്പോൾ ഇൻ്റഗ്രേഷൻ ഫ്രം 0 to log y f of x dx. Then also you can find directly which is equal to log y. You may try it yourself. Okay, now again we come to the cumulative distribution function of y. Cumulative distribution function of y known ആണെങ്കിൽ നമുക്ക് ഇതിനെ ഡിഫറൻഷ്യേറ്റ് ചെയ്യാവുന്നതാണ്. പക്ഷേ ഇവിടെ ഡിഫറൻഷ്യേറ്റ് ചെയ്യുമ്പോൾ ഒരു കാര്യം ശ്രദ്ധിക്കണം. ഈ കുമുലേറ്റീവ് ഡിസ്ട്രിബ്യൂഷൻ ഫംഗ്ഷൻ എന്ന് പറയുന്നത് ചിലപ്പോൾ കണ്ടിന്യൂസ് ഫംഗ്ഷൻ ആയിക്കൊള്ളണമെന്നില്ല. അല്ലെങ്കിൽ ഈ വൈയുടെ ഡിസ്ട്രിബ്യൂഷൻ ഒരു കണ്ടിന്യൂസ് റാൻഡം വേരിയബിൾ ആയിക്കൊള്ളണമെന്നില്ല. ചിലപ്പോൾ അതൊരു മിക്സർ ഓഫ് ഡിസ്ട്രിബ്യൂഷൻസ് ആയേക്കാം. അപ്പോൾ അതുകൊണ്ട് ഡിഫറൻഷ്യേറ്റ് ചെയ്യുന്നതിന് മുമ്പ് ഇത് ഒരു കണ്ടിന്യൂസ് ഫംഗ്ഷനാണോ എന്ന് വെറുതെ ഒന്ന് ചെക്ക് ചെയ്ത് നോക്കണം. സംശയമൊന്നുമില്ല, കണ്ടിന്യൂസ് ആണ്. കാരണം അത് വൈക്ക് 1 കൊടുക്കുമ്പോൾ ലോഗ് വൈ ആണ്. ഓക്കെ, വൈക്ക് 1 കൊടുക്കുമ്പോൾ അത് ലോഗ് വൈ ആണ്. ഇനി വൈക്ക് 1ൽ തൊട്ട് താഴെയുള്ള വാല്യൂ കൊടുക്കുമ്പോൾ അത് 0 ആണ്. ഓക്കെ, if y is you can see this, y is 1 to e. Okay, then you can see that when you put y is equal to 1, it is log y, that means 0. So in this range, in the first range as well as in the second range, you are having the same value for fy of y for y is equal to 1. And similarly here log e, that is equal to 1. Therefore, because of the nature of this function, it is continuous. Okay, and hence the PDF can be determined quickly, immediately by differentiating this distribution function. So fy of y is equal to the derivative of f of y, that is f prime fy of y, that is equal to 1 by y for y lying between 0 and e and equal to 0 elsewhere. കാര്യം ലോഗ് വൈയുടെ ഡിഫറൻഷ്യൽ എന്ന് ഡിഫറൻഷ്യൽ എന്ന് പറയുന്നത് എന്തായിരിക്കും? 1 by y ആയിരിക്കും. ഇനി 1ൻ്റെ ഡിഫറൻഷ്യലും അതുപോലെ 0ൻ്റെ ഡിഫറൻഷ്യലും ഒക്കെ 0 ആണ്. അപ്പോൾ അതുകൊണ്ട് ഈ റിസൾട്ട് നമുക്ക് കൺസോളിഡേറ്റ് ചെയ്യാം. ദിസ് ഈസ് ഈക്വൽ ടു the density function is equal to 1 by y for y lying between 1 to e and equal to 0 elsewhere. ഇവിടെ നമ്മൾ കണ്ടിരിക്കുന്നത് എന്താണ്? നമുക്ക് എക്സ് ഒരു യൂണിഫോം ഡിസ്ട്രിബ്യൂഷനാണ് എന്ന് തന്നിട്ടുണ്ട്. എന്നിട്ട് ഇ ടു ദി പവർ ഓഫ് എക്സിൻ്റെ ഡിസ്ട്രിബ്യൂഷനാണ് നമുക്ക് കാണേണ്ടത്. അതിനുവേണ്ടി നമ്മളിപ്പോൾ ചെയ്തിരിക്കുന്നത് എന്താണ്? നമ്മൾ ഡിസ്ട്രിബ്യൂഷൻ ഫംഗ്ഷൻ ഓഫ് വൈ കണ്ടെത്തി അതിനെ ഡിഫറൻഷ്യേറ്റ് ചെയ്തു. ഇതാണ് വളരെ സിമ്പിളായിട്ടുള്ള പ്രൊസീജിയർ. ഇനി അതേപോലെ തന്നെ മറ്റൊരു എക്സാമ്പിൾ കൊടുത്തിട്ടുണ്ട്. ദ സെയിം പ്രോസസ് ഈസ് റിപ്പീറ്റഡ് ഹിയർ. ഇവിടെ എക്സ് ഫോളോസ് യൂണിഫോം ഡിസ്ട്രിബ്യൂഷൻ -1 to 1 and a function is defined as y is equal to g of x which is equal to x square, and we have to find the CDF and PDF of y. ഇവിടെ ഈ സ്ക്രിപ്റ്റ് എക്സ് എന്ന് പറയുന്നത് -1 to 1 ആണ്. അതുപോലെ സ്ക്രിപ്റ്റ് വൈ എന്ന് പറയുന്നത് നമുക്ക് കണ്ടെത്താം. ദാറ്റ് ഈസ് ഈക്വൽ ടു സെറ്റ് ഓഫ് എക്സ് സ്ക്വയർ ഫോർ വിച്ച് എക്സ് ലൈസ് ബിറ്റ്വീൻ -1 and 1. സോ ദാറ്റ് ഈസ് ഓൾസോ ഈക്വൽ ടു 0 to 1. ദാറ്റ് ഈസ് ഈക്വൽ ടു 0 to 1. എക്സിൻ്റെ റേഞ്ച് -1 to 1 ആണെങ്കിൽ വൈയുടെ റേഞ്ച് 0 to 1 ആണ്. ഓക്കെ, നമുക്കറിയാം ഇതിൻ്റെ ഡെൻസിറ്റി ഫംഗ്ഷനൊക്കെ നമുക്ക് കണ്ടെത്താവുന്നതാണ്. ഡെൻസിറ്റി ഫംഗ്ഷൻ of uniform distribution over -1 to 1 എന്ന് പറയുന്നത് എഫ് ഓഫ് എക്സ് ഈക്വൽ ടു 1/2 -1 ലെസ് ദാൻ ഓർ ഈക്വൽ ടു എക്സ് ലെസ് ദാൻ ഓർ ഈക്വൽ ടു 1 ആണ്. ജനറലി സ്പീക്കിംഗ് യൂണിഫോം ഓവർ എ ടു ബി ആണെങ്കിൽ ഡെൻസിറ്റി എന്ന് പറയുന്നത് 1/b മൈനസ് എ ആണ്. അപ്പോൾ ഇവിടെ എ എന്ന് പറയുന്നത് -1 ബി എന്ന് പറയുന്നത് 1 ആണെങ്കിൽ 1 divided by 1 minus of -1, that is 1/2. That is how this density is 1/2 for x lying between -1 to 1 and equal to 0 elsewhere. ഇനി അതിൻ്റെ ഡെൻസിറ്റി ഫംഗ്ഷൻ ഉപയോഗിച്ച് നമുക്ക് ഡിസ്ട്രിബ്യൂഷൻ ഫംഗ്ഷൻ കാണാം. ഡിസ്ട്രിബ്യൂഷൻ ഫംഗ്ഷൻ എന്ന് പറയുന്നത് എക്സ് പ്ലസ് 1/2 ആണ്. That you can easily find out. Okay, so distribution function can be consolidated like this: fx equal to 0 for x less than -1, the lower limit of x, equal to x plus 1/2 for x lying between -1 and 1, and equal to 1 for x greater than 1. Okay, now the range of y is simply 0 to 1, and in order to find the distribution function of y, you know that when y is less than 0, fy of y is equal to 0, and for y greater than 1, fy is equal to 1. This result is obvious. Okay, and then for y lying between 0 to 1, you can find the distribution function directly using this probability that minus y root y less than or equal to x less than or equal to root y, that is equal to fx of root y minus fx of minus root y, because probability that a less than or equal to x less than or equal to b is nothing but f of b minus f of a, right, for continuous random variable. And you can see that fx of root y is root y plus 1/2 minus, then this is root y minus root y plus 1 divided by 2, and you will see that it is equal to root y. Okay, so summarizing, the distribution function is this, and then you find the differential derivative of y, that is equal to 1/2 root y, because here f of y is equal to root y, so its differential is 1/2 root y, and for 0 and 1 the differential is 0, therefore the density function is consolidated like this: f of y is equal to 1/2 root y for y lying between 0 to 1 and 0 elsewhere. Okay, this is the method we usually apply for in many cases. In many simple cases, you can directly apply the method of finding the cumulative distribution function and then differentiating that CDF. But we will see that some general procedure is there for finding the distribution of function of a random variable. That method is called method of transformation. In the next video, we shall discuss the method of transformation of finding the distribution of function of a random variable. Okay, thank you.